Some earthquake basics before you do the Earthquake Epicenter Magnitude Lab. First, an earthquake is simply a sudden rupture of the ground, of the Earth's crust. It's much like a tree branch that when you bend it, you're putting strain on it and you're storing energy in it, potential energy. And if you bend the branch too far, it will rupture and snap, break, like a meter stick that you bend too far. Same for the Earth. The Earth will bend and build up that strain, and then when it can't bend anymore, it will rupture, and that rupture is the earthquake, and it releases the energy in the form of seismic waves, which we feel as an earthquake. The most important anatomical features of an earthquake are the focus and the epicenter. The focus is a place inside the earth where the earthquake actually happened. That could be, hundreds of meters down, or it could be hundreds of miles down. And the epicenter is the point directly above it. So you cannot stand at a focus, but you can stand directly above it on the epicenter. Okay. There are lots of types of seismic waves given off during earthquakes. These are just four of about 13 that I'm familiar with. The P waves and the S waves are body waves. They pass through the inside of the earth. P waves are the push-pull waves, like a slinky that you're pushing and pulling on. And an S wave is more of a snaking wave. And there's love waves and Rayleigh waves. These are surface waves. They're not the same as body waves. Body waves can pass through the interior of the earth. Love waves and Rayleigh waves only travel on the surface, and they do all the damage. Fortunately, they don't travel very far. Otherwise, an earthquake would happen and the whole country would fall down. If you want to see animations, if you want to see animations of these types of waves, you can click these links in this presentation. It's linked on Blackboard on this above the videos. But let's take a look at the seismometer. The seismometer is how earthquake waves are recorded. You have a device that's bolted to the ground, and inside it, on two large or very stiff springs, is a heavy mass, this cylinder. The idea is simple. If the earth shakes and this is bolted down to a slab on the earth, this will move back and forth, but that weight will not want to move. Okay, and the relative motion between a sensor in this cage and on that on that cylinder is picked up as an electric impulse, and that is what helps it transcribe that into a line, or the squiggly line that you are familiar with as a seismogram. Okay, but it's based on the idea that an object at rest will stay at rest unless acted upon by an outside force. So since this is suspended in the air above the base and not really physically attached to the earth, the cylinder doesn't want to move, and the base does move attached to the earth. A seismogram for a typical station actually measures horizontal east-west and horizontal north-south, and it also measures vertical motions. But if we just focus on this top one here, we can see the arrival of the P wave and the S wave. The difference in time between the P wave and the S wave are important for determining the distance to an epicenter, the distance to the earthquake. So this statement here just explains how the seismogram works again. It's everything I just said. So you can take a look at that presentation if you need to review this. I wanted to skip ahead here to P and S wave arrival times. This is a common chart that you'll see. We're not going to use this chart, but I want you to understand what it tells us about the P waves and the S waves. Let's say you have an earthquake at some time 0. Start the stopwatch at the moment you have an earthquake. Take a look at this for a second and go up to about 6 minutes. You can see that in 6 minutes the P wave has been able to go 2,000 miles. How much longer will it take for the S wave to travel that far? The S wave, it takes 11 minutes for it to travel that same distance. So you can see that S waves are much slower than the P waves, And it's this difference in time, kind of like the difference between lightning and thunder when you're listening to thunderstorms to determine how close you are to the lightning strike. This is the same idea here, where the blue line is the lightning and then the red line would be like the thunder. Okay, and this is how we're going to use it. We're going to determine the S and P intervals. This chart will make things a little simpler because we're going to do the math to determine the P and S wave interval, and then just find that difference in time between their arrival times, and then get the distance. So let's say we had 6 minutes between the P wave and the S wave. So you come over here on this and follow that over, and then come down, and it's about 4,000 miles. Okay, and that's from knowing just the difference between the P wave and the S wave arrival times. Okay, now that's for one station. If we do that for 3 stations, if we get the P minus the S arrival times and then use that to find the distance for 3 different stations, so this would, each of these red dots is a seismic station. If we then measure that mapped distance out away from that location, that city, and then draw a circle, and we do that for the other 2 cities, you'll see that, or seismic stations, you'll see that they cross a couple of times, but only in one place do all 3 of them cross. And where all 3 of them cross, that's where the epicenter is. This is called triangulation. Okay, so now we're into the lab. This is a review here. P wave arriving here, and the S wave arriving here, and the difference in time, the S minus the P interval, is the time it takes, the time that passes between the arrival of the P wave and then the arrival of the S wave. And we can calculate this pretty simply by looking at the this little note down here that shows the 20 seconds for each one of these blocks. Okay, so if we have the distance, if we know that this is 20 seconds right here, and another 20 seconds, and another 20 seconds, and another 20 seconds, you get the idea. We can add up all the seconds between the P wave and the S wave. Okay, so let's try that down here a little bit later, down on this one. I'm gonna do the first one for you, and then you'll do these on your own. Colorado, Denver, Colorado, and Sacramento, California, you do on your own. Okay, so let's take a look at this. We're going to say that this arrival time right here is where it started. It's right at the edge of this yellow. That's where the P wave arrived. Okay, and then the S wave didn't arrive until here. All right, so how many of these boxes are there between the P and the S? So if you go across here like this, this is the distance right here, all the way to there, right up and down there. Okay, so this would be 20, 40, 60, and so on, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 times 20. What is that? 340 seconds? Let's see. Yep, 340. So 340 seconds is your S&P lag time. Okay, so we don't know the distance yet, but we can get that using this information, using the 340 seconds. Okay, so we come down here, got to go past the map, go all the way down here, and I can't draw on top of this chart, but we can try with the pointer here. So there's 330 seconds, there's 360 seconds. So 340 that's 350 right there in the middle between those two. So 340 is about right here, 350, then 360. So 340 is about right here. And it looks like it's about 4,000. It's really close. About 4,000 kilometers at 340 seconds. Okay, so you should write 340 seconds in this S&P lag time window, and then 4,000 kilometers in the epicenter distance box here. These aren't probably super precise, but we should still get a reasonable result because we have two more stations to work with to help us. Okay, so the next thing we do is we have to figure out what the magnitude of this earthquake was. And to get the magnitude of the earthquake, we have to look at the arrival over here of the S wave. And we are interested in the highest spike, either below or above this flat line right here. See where it says 0 millimeters? We're interested in this scale on the right now, and we want to find the highest point. And the highest point is about right here where the pointer is resting right now. And if you come over here to the side, right over here, it's about 10 millimeters right here, 10 millimeters high. Okay, so now we're going to use that information to figure out what the magnitude of this earthquake is. You'll notice that magnitude is in the middle. This is a chart called a nomogram. The magnitude is in the middle. The epicenter distance and the S&P interval are over on the left side, and the maximum S wave amplitude on the right. So if you notice up here, 4,000 kilometers in 340 seconds, which is, there's 341, it's about where we were. So if you have this point marked, and you have 10 over here, 10 millimeter amplitude, it's a matter of drawing a straight line. I'm going to have a hard time doing it, but I'm going to try. And it would basically go across. That's not working, but you get the idea. I'm trying to come over here like this, and I'll try it again. It's going to be impossible, but I'll try to do a better job. I'm going to go straight across. Didn't work. Anyway, when you'll use a straight edge, and when you come across here, see how this green line is straight. One over here you have 100 for the distance, and over here you have 1 millimeter for the height. And then when you draw the line across, where they cross, where the line crosses the center here, that's the magnitude. And if you've done this correctly for all three stations, they're all going to cross at the same point. Okay, they're all going to cross in the same area. So if I've done this correctly, the other ones should be crossing up in this area also. But remember, use a straight edge because this is not how to do it. Okay. So the last thing you're going to need are your three distances that you have for each of the seismic stations. And when you are ready to do this, you have a map here and a scale. And watch the next video, video number 2, for instructions on how to use the distances that you determined for each of your seismic stations in the United States, and then draw the circles on the map and look for that place where they intersect, where all three intersect, to determine the epicenter. Again, this is all explained well in video number 2.